Okay, let's do the implementation. So we have the piece, which is actually completed. We have the game, which is actually not completed. Let's start from the game. So first of all, we need to initialize the board. So in that case, let's say board equals new board. But in that case, we should ask the number of rows and number of columns, because in the default case, the row count is 6 and column count is 7. So let's ask number of rows, system out print, and let's have a scanner input equals new scanner system.in. And let's say we have the row count and column count. So row count, column count. And let's say we have row count equals input dot next int. And again, number of columns. We have input dot next int for column count. So in that case, we also could check if the row count and column count are, if they are less than 4, both of them should be larger than 4. So we can say while row count is less than 4 or column count is less than 4, both of them should be larger than 4. In that case, they should enter row and column. Or we can do while loop here. Do system out parent line and do while something like this. Okay, so we have the row count and column count for the board. And then we ask to play. So in the play, we assume we have the first player, which is actually the human player. In that case, we can ask actually again system out parent line, enter your name as human. So let's say string name. Again, let's take the input from the user. For this case, input dot next. And then we can create our first player, which is actually new human player. So it should have a name, and let's say it is blue. And then we have the player 2, which is actually a computer player. And what will be the computer player's name? Let's say computer, and the color is yellow. And let's say the level is, for now, let's say 1. So for simplicity, let's say. And then we have the player 1 and player 2. And now we can start the play. So first player 1 should play. Player 1 play with the board. And in that case, it will update the board. So then player 2 plays with the board. And we should do this, do while board game over, not game over. So in that case, or we can do something like this. We can have while true, and we can say player 1 play. If board game over, we do something. Or we have player 2 play, and again, if board is game over. So we can have a break here. And also at the same time, if board is game over, it can be due to everything is played, or let's say, etc. Then the thing is, we should check whoever wins the game. So board, winner of the game. So switch, board, winner of the game. So if it is blue, then which is our name. So player one get name wins the game. Or case yellow, system out print line, player two wins the game. And the default case, system out print line, there is a draw. And then we finish. Okay, let's run the game, which is maybe not possible now. Let's do some dummy things. Here, return true, game over. Winner of the game, return blue, let's say. And return 0 here. Return 0 here. And is full, return false here. Okay, so in that case, let's start the game from the main. So let's run the game. Just for checking, number of rows, 6, number of columns, 7, enter your name, Olcay. Olcay wins the game because it's directly game over. Okay, let's also print the board. So, which is actually printing the board is here. So what will we print? First of all, we should print the row by row. So, and we should first print the last row, which means integer I equals row count -1, I larger than equals 0, I minus minus, so which is the last row actually. And we should print the columns one by one. So integer j equals 0, j less than column count, and j plus plus. So then we should print the board pieces. So in that case, we should give piece a toString. So string to string public. So public string to string. So let's say switch color. So if it is blue, you return O. If it is yellow, you return X. And the default case, you return empty string. Okay, so we can modify it later to have maybe a different field space, field circle, possibly. Field circle, Java. Code. Which we actually don't know. there is something like this. Do we have a Unicode for that? We don't know. So let's make it X. Okay, so that's for the piece. And then we can do actually a string here, row, which is empty. And then we can have row plus equal board ij to string. And we can do it with string builder, and at the end, s out actually row. So that's the thing. Maybe we can also print. Okay, so let's print the board. So after each play, we should print the board. So actually before the play. So let's say board print. And then we print board. Okay, let's run it again. Number of rows, 6, number of columns, 7. Enter your name, Olcay. Olcay wins the game. So as you see, there are no pieces. So in that case, we print empty strings. Okay, so that's actually the board, printing the board. So let's then continue with the human play. So the human should play something. So let's play for human something. So let's ask something for human to play. So scanner input equals new scanner system.in, and we ask the number of the column index. So enter the column index, and integer column equals input dot next int. So we also should check if the board that column is okay. So do while board is full column. So what is this? So it's actually int column. Okay. Do while board while the that column is full. Okay, then we may maybe replace this with is column full. Okay. So in that case, if it is full, then you cannot play there. So otherwise, you can play return column. Let's also code that. So which means we have board row count -1, which is the last row. Column no is not empty. Get color is not empty. Okay, so then what will computer play? That's interesting. In that case, let's see how it goes on. So again, 6 rows, column rows, Olcay, enter the column index. Let's say I play 0, but Olcay wins the game. So let's Olcay board gamer. Let's make it false and see what is going on. So 6, 7, Olcay 0, which is actually not seen. So why didn't we see? Because if the human or computer place, we actually should take the column. So let's do column equals board and also column equals that. And then we should update the board actually. So in that case, play column count. So we should update the that column. So what will we do? We should check if the if that column actually from the 0th row to until row count, we should check if the board I column count, actually not column count, maybe column row, no. Okay. Column no get color is empty, then in that case we update okay, so we should update this equals new piece color. Okay, and then we break. We don't forget to break. So we update it with that column with that color. So let's go to game and then board play column, and the first player's color is blue and the second player's color is actually yellow. So then let's see what is going on. So 6 rows, 0 rows, Olcay, and let's see column index. As you see, we enter 1. So the computer always plays, as you see, the 0th column. So it's going good. So it will continue actually. So let's play. So the computer actually cannot play basically, but the thing is it's not so important. Okay, so maybe we can modify the print case. So as out computer place. So we can print something like this. And we can say, yes. Case human place. Okay. 6, 7. Olcay, human place. Let's see, 0. Human place. 0. Etc. etc. Okay. So that's it. And in the column, actually we can change it because it's actually starting from 0, something like that. So maybe we should actually drop -1 and also something like this. So actually we should say column 1. So Olcay. So 1 is actually that. 0. Aha. Is column full. So we should also check if the column is valid. So column is less than 0, less than equal 0, or column larger than column. So the board's column count. Board get column count. Or So larger or equal. So let's say. So in that case, if the user enters 0, it will ask again 7. Actually, it can say 7. So because it will be 1 minus. Okay. So we changed actually the play. So maybe we can also print numbers below the string. So that's actually will not be good. But the thing is, okay, we may do something like this. Integer I equals 0, I less than column count, I plus plus, S out, I plus 1, something like this. And then we will print direct exactly. Okay, maybe we can now do better screen. So as you see, 1, 2, 3, 4, 5, 6, 7 shows the columns. And we can play, for example, 2. And now you can see the column numbers. So that's actually some makeup. Okay, so we have print. We are actually almost okay. We should also check if the game is over or not. So in that case, we should check if there is 4 in a row. So let's start writing 4 in a row. So in that case, we should check every cell. So for integer, I equals 0. Let's start from the bottom row, row count I plus plus, and we actually check which directions, left and right. Actually, not left, always right. We should check always right, and we should always check up, and we should always check upper right diagonal. So we go like this. Okay, so in that case, we don't need to check. Okay, we may check all rows. So because we go right. So for integer, j equals 0. So j goes to column count j plus plus. Okay, so that's actually now the start cell, let's say. So first of all, if we check if that cell is not empty, if that cell is not empty, then we start checking in 3 ways: up, right, and diagonal. So let's do that. So let's do color, cell color equals board I and j get color. So this is actually that cell's color. So given that cell's color, what will we do? We go right, check right, and we go check up, and we go check diagonal. So we can actually write those as 3 functions. Maybe we can utilize also that in 3 in a row. So okay, let's write a private function, public boolean, check right, row no, and column no, and we have the color. Okay, so what does it do? It checks how many right as the right direction we have that many pieces. So let's also call piece count. So if you have that many pieces at that direction, then it will return true. Okay, so if we do check right, then what will we do? For integer I equals 0, I goes to piece count, and I plus plus. So since we will add 1, we will do something like this. Start from 1. And if, since we are going right, the column no will increase. If the column no plus I is larger than or equal the column count, then we return directly false. Because we go outside the boundaries. So if it is not, then in that case, we check if the board row number and column no plus I get color equals color. If it is not, we also return false. So otherwise, we return true. So what we are checking, we are going to write for a given row, and we go right to check each number of pieces. Okay, so that's actually check right. We need to also check up and check diagonal. So let's write them down. Check up. In the check up, we again have piece count. In that case, row no plus I is larger than row count, etc. And row no plus I plus column no equals color. Then in that case, we return false. Okay. So we should also check diagonal. So let's check diagonal. Check diagonal. So in that case, if row no plus I or column no plus I is larger than column count, we return false. Again, if row, if this one is okay, then okay, column no, not equals the color, you return false. Okay, so we check right, we check up, and we check diagonal. Okay, so 4 in a row. So if then check up I dot j dot the cell color, and 3, if we have 3 more pieces, then you return cell color. And similarly, if we have check right and check diagonal, we also return cell color. Okay, so 4 in a row is almost okay. So let's run the game if it checks correctly or not. So let me. So that's actually 4 in a row. So the game over. Where was the game over? So it actually returns board, not board, what, 4 in a row. So 4 in a row is not empty. Empty. Then it's game over. Also, we should check full. Where is it? Check full. Okay, so we can say if 4 in a row is not empty, you return true. Otherwise, return false. We also should check if the board is full. In that case, let's do for integer I equals 0, I less than column count, and I plus plus. So in that case, if board is empty, yes, that column's color is empty, then it cannot be finished. Otherwise, it is finished. Okay, so this one actually checks full of board. So each cell should be, each column, if one column is empty actually, then you return false. Otherwise, you return true. Okay, so let's see the code. So 6 columns, 6 rows, Olcay, and let's play. So let's play to win. So Olcay wins the game. So let's play to lose. 6, 7, Olcay, 1, 7, 4, and 7. The computer wins, but we didn't see it. How is it possible? So it actually passed it. So let's put another 7. Actually, computer wins. So how we didn't check it? So did we? Or checkup is wrong? What is the problem? So we didn't check it, or so let's check this. So 6 rows, 7 columns, Olcay, and let's play 7. Let's continue. Let's play 4. Let's continue. Let's play 2. Let's continue. Let's play 7. Okay, so the board we have now as the board 0th row we have X, first row we have X, second row we have X, third row we have X. So it should actually find it. So board in a row, 0, 0, cell color is yellow. Okay, check up. So it's actually returning correctly. So cell color, game over. Actually it worked, but we didn't understand it. So that's 6, 7. Olcay 7, 4, 2, 7. Okay, so actually not Olcay wins the game. Actually, the computer wins the game. So what is the problem? In that case, fourth winner of the game. Okay. So here actually we should return 4 in a row. Okay. So that's actually what we have done incorrectly. So we now have 4 in a row and column count. So we are playing. almost correctly. So we have row count, column count, winner of the game, play, print, check right, check up, and check diagonal, 4 in a row, etc., etc. So now let's come to the computer. So the computer player will actually create its on board. So what does it mean? So when it plays, actually, it should construct the state. So let's construct the state. State equals new state with the current board. And then actually we should clone the board. Otherwise, we actually should update each time the board. When we update the board, then it is a big problem. So let's write a clone method to board. So public board clone. So which actually should be something like this: board clone equals new board row count and column count, and then we copy actually to the clone. So clone dot board equals actually board ij, or we can also create new pieces. So get color. Then we return the clone. Okay, so we have the clone. So then in that case, we can actually create the clone for the new state, so that we will not, if we modify the board, this will be a modified board. Okay, so we have the state. We have the state, and the state has actually initial board. So now we generate actually state generate tree of moves with level. So let's then write it. So then what will we do? So the thing is, given the current board, we will try to play for every column with the current board. And if that column move is okay, then we add to the next state. So let's first create the next state. So we have new array list, and then we check for every column. So I goes to current board get column count, and if is a current board column is not full, because if it is not full, we can actually play for that board. So current board play to that column, but which color? That's important. So since we are yellow, according to the level, the color will change. So so in that case, so for the first level, but first shows, okay. So there are possible alternatives. So we can, for example, say something like this: integer level max level, and we can say one level. So in that case, if the level is 1, then we should play. If the level is odd, we should play ourselves. If the level is even, we should play as the human. So then if level mod2 equals 1, then we should play as ourselves, which ourselves means as computers. And what was the computer's color? It was yellow, I think. Then we should play as yellow. Otherwise, we should play as blue. Okay. And actually, we should clone the current board. So which means, so we have board, child board, which is actually current board's clone. And then we will play as the child boards play, and then create new state and add it to the next state. Next state's add, new state, child board. So now we create new child board as the current board's clone, and we play accordingly. So if the level is 1 or 3 or 5, we play as computer. If the level is 2, 4, etc., we play as humans. Let's see. Okay, so computer plays yellow. So actually, do we have the color of the player? So we have the color of the player actually. So we don't need to do that. So which means, so player 2 get color, player 1 get color. So then we can modify this as state. Okay, but we didn't give this as okay. Okay, so we have the generated next state. So then what will we do? We will generate next states, and then for each state in the next states, if the level is actually, if the level is less than equal, so if the level is larger than max level, or not like that, we can say here, if the level is less than max level, so then we should, for each state, call generate next 3 moves. So for each child state in next states, we should call child state generate 3 of moves level +1 and max level. Okay, so level increases and you call generate next 3 moves. So let's, okay, so it will not currently calculate the best move, but it will do the analysis. So let's play. So he played, and we win. Okay. So it generates. So currently, where is the computer player? It's the level. So let's, for example, create the level not 1. Where was it? Actually here. Let's create, for example, 5. So will it be fast? Let's see. 6, 7, Olcay. and enter column index. So it's fast actually. So it's creating. Okay, not bad. Or is it correct? We will see. Okay, so then we generate tree of moves. And then after that, we actually get the best move. So return state get best move. Okay. So get best move is actually returns 0. So let's see get best move. So in the get best move, what will we do? In this case, we should evaluate the states, and accordingly, we should decide what will we play. So for each state, so we are now in the current state. So we should check the best move for this state. So then the thing is, we can write this as a recursive function again as the level. So so again as the level and max level. So let's go to computer player, one level. Okay, let's go out this game. Player is okay. We have here. Okay, so so if the level is odd, then we need to find the points of its children and then check. So we play as the first level to improve our performance. Then the human player will play its move to decrease our performance. So in that case, if the level mode 2 is 1, we should maximize our score according to the states scores. And if the level is even, we should minimize the scores. And other than that, okay, so, but the problem is the level scores should be calculated first. So then so we can actually calculate the scores of the boards when we generate tree of moves. So let's say okay, so here, if the level equals max level, then we should evaluate the child scores. Okay, so the state should have also a score, first of all. Okay, so let's get a score, private int score. Okay, so how will we score? Depending on the evaluation function. So in that case, let's also give it as a evaluation function type so that we can modify it later. So evaluation function type, evaluation function type. This evaluation function type equals evaluation function type. So in that case, the computer player should also have the evaluation function type. So private evaluation function type, evaluation function type. So this evaluation function type equals evaluation function type, and we should call the evaluation function type here. And for the related one, let's say simple evaluation function type simple. Okay, so let's come here. We have the evaluation function type. So let's call the evaluation function type. So in that case, the evaluation function will return actually the score. So which means for state, child state, in next state, child state, so child state, current board, or in that case, let's say switch, evaluation function type. So new simple evaluation function, evaluate child state current board. So score equals this. So why does it give? Because it's actually case simple. So for simple evaluation function, we create a simple evaluation function and evaluate it. We can actually give this as a parameter. That's also possible. Each time we are creating functions, but let's not do it now. Maybe we can do it later. So complex evaluation function, we calculate it with complex evaluation function. Okay, so we with simple evaluation function we evaluate the board. With complex evaluation function we evaluate the board, and then depending on the scores for the levels, we should go up and check the scores of the game. So we have the scores now for each child. So then we should check if the level is, so in that case we should do something like this. So if the level is not max level, if the level is not max level, we should call get best move of all next states. Actually, it's not like that. Okay, so what will we do? So if the level okay, so maybe we can do this. So we generate tree of moves for the child states. And then Okay, what will we do? So the thing is, when we call generate tree of moves, we can also set the scores, and also for other levels, we can check if the minimum is accomplished or not. So let's say the max level is 1. So in that case, level is 1, but the maximum is 2. And also the evaluation function should consider the values. So we are stuck here. So the evaluation function actually should consider the color. So in that case, let's also change it. So color. So let's modify it. So simple evaluation function, color, and complex evaluation function, color. And where do we call it? Actually, we call it here. So accordingly, depending on the level. So if the level is odd, then the color is, let's say, color is yellow. Okay, so we can do something like this. Okay, so let's put it here. Color, current color is yellow, and current color is blue. So then now we will put a current color here. So now that will be current color and current color. Okay. So when we calculate actually the evaluations, so what will we do? We generate the 3 moves, generate 3 of moves. Let's say we have level 1 and max level is 1. So in that case, we calculate the scores for us, and that's done. But let's say the level is 1, but max level is 2. So in that case, we generate 3 of moves for children. But in that case, we after creating it, depending on the level again, if it is 1, so for level 1, we should take the maximum of its children, actually. So, or minimum. So we create the states, child states, and then okay, so 1, 2, 3, it will be something like this. If the level is odd, we find the maximum of our child states to score or state. If it is not, we get the minimum of them. Okay, so then let's get the integer min score. Min score is, let's say, integer max value. Let's put it 1000. And then for state, child state, from next states. So let's say in that case, if the child state's score is less than min score, then min score equals child state score. And then we set our score to min score. Otherwise, we take the maximum. So in that case, let's put our max score minus 1000 and max score, if our score is larger than, then we have the max score. Okay, so when we generate the tree of moves, after we generate tree of moves, we get the minimum or maximum depending on the current situation, and otherwise we score it. Okay, so then the get best move actually do not need anything at all. It just returns the maximum of our scores. So which means actually it is like this. So what will be the move then? So in the state, we should also store the move. So in that case, we should also set the move so that we can know which was, okay, the maximum score, but best move. So best move is -1. So best move is child state move. So return best move. Okay, so we have the best move here identified. So we also should set the best move. So in that case, let's do state child state equals this one. Child state move equals I, because we are moving to that state. And then we have the add states, child state. It is now a large okay, so then we can do something like this. Private maybe we can do something like this. State min child state, which actually does something like this. Min score state min child equals child state, and we return min child. which is null at the beginning. So state best child, mean child state, and then we return best child score. Okay, so then similarly, we can find the max score for that. So let's find private state max child state. So in that case, we will do something like this. And max child. Max child. Max child. Max child equals child state, and we return max child. Similarly, we have best child, max child state, and best child score. So we can say state best child here, best, and we can put it here. Okay, so we have the best child, and similarly, we can have get best move as state best child, max child state, and best child move. Okay, then that should be a good alternative. We put the code a little bit smaller, although not so small, but a little bit small. So then what will we do? We should write the evaluation functions. Okay, so for the simple, let's start with the simple evaluation function. For the simple evaluation function, we should check something like this. If the board, so it's like this, if the color is blue, okay, so first we should check or 4 in a row. So if there is a so color, win color. So if there is a win color, so if the color is win color, then you return maximum, which is 1. Actually, it's like this. If the color is so if the color is win color, okay, so if the color is empty, you return 0.5. Should not 0.5. Let's make it 5. If the color is win color, you return 10. Otherwise, you return 0. So 5 will be draw. Win color will be 5, and the other will be 0. Okay, so let's build the project. No problem. So let's play the game. For